questions. So let's get started here. Chemistry 3101. This is where we kind of left off last week as we were talking about the chemistry of alcohols, and we looked at substitution and elimination reactions of alcohol. So it says predict the major product for each of the following reactions. Well, we know that when we take a tertiary alcohol, and that's what this is. So let me get my red pen here. We have a tertiary alcohol, and we're treating that with HBr. Well, if you go back in our slides, okay, we said way back here that when we take a tertiary alcohol and we treat it with HBr, we end up making the tertiary bromide. So you could just, write out the product and say, well, I'm going to get this. I have my cyclohexyl ring here, my methyl, and now I'm going to replace that that hydroxyl rather with a bromine. And this is an SN1 mechanism. Now, I'm not going to take the time to draw it right now, because we're going to take a look at some examples where we draw some mechanisms like this in a few seconds. The next one is, again, one of my favorite reactions in organic chemistry. When you take a tertiary alcohol, all you got to do is treat it with some sulfuric acid and crank the heat up. And again, if you go back in our notes here, that's what we talked about right here on this page. Okay, we said if you take that tertiary alcohol and you heat it up in acid, you always end up with the Zaitsev alkene. So there's two possible alkenes you could make here, right? You could make the Hoffman alkene if you made the double bond here, but if we make the double bond here, then we have the Zaitsev alkene, and that is the product that we're going to form. And again, you could practice drawing the mechanism of that. So here is our Zaitsev product. So again, that's going to be the major product, or really the only product if you heat it up enough. So this is an E1 reaction like that. So we'll put here always obtain the Zaitsev product. So something to remember there. Again, one of my favorites. Any reaction where all you have to do is throw in some sulfuric acid and heat it up, that's a fun reaction, okay? Very little work required, okay? Anyhow, let's take a look at question 7.43. Now we're asked to draw some mechanisms for these same types of reactions, right? The first one is an SN1 reaction. We have that tertiary alcohol, and we're treating it with HBr, and we're replacing or we're substituting the hydroxyl for a bromine. So again, an SN1 reaction. Well, let's draw out the HBr molecule first. So the first step is going to be our proton transfer. I'm going to throw a couple of lone pairs on my oxygen like that, and then I'm going to draw the proton transfer just like that. And then what I'm going to end up with is something that looks like this. So let's draw the intermediate. I'll draw it down here just in the interest of space. So we're going to have this like that, and then we have the ethyl group here. Now you see the way that I've drawn the protonated hydroxyl like this. This is kind of a shorthand of drawing the whole Lewis structure, which either way is acceptable. I mean, you can do it like that or like this, but either way, now we've created what? We've created a good leaving group, because if water leaves, water is the conjugate base of hydronium, which is a strong acid. So we can have our leaving group leave like that, and then we end up with a tertiary carbocation. Well, what's going to happen with that tertiary carbocation is that the bromide we made in the first step is going to be able to come in and act as a nucleophile. So I'll draw my bromide, throw in all my lone pairs here, and then I'm going to get the nucleophilic attack of the bromide to the carbocation, and that gives me my final product just like that. Let's try drawing a mechanism for the next one. This is an elimination reaction. This is an E1 reaction. And you notice that if you take a quick peek at the carbon skeleton, right, here's our carbon skeleton, you notice that it's changed, hasn't it? So that indicates there must be some kind of rearrangement, right? So let's draw what the intermediate would look like. And then, yeah, we'll be able to figure that out. Now, for the proton transfer, in the first step, you could take the time and draw the entire Lewis structure of sulfuric acid out. So this is the Lewis structure of sulfuric acid, and you could draw the proton transfer, occurring like this. That's no problem. But remember that when we put sulfuric acid, or when we have sulfuric acid, even when it's concentrated, is still in water. Okay, it's got a molarity that's like 18 molar or something. So remember, and this goes back to the acids bases chapter, if you have water and sulfuric acid, H2SO4, the equilibrium is mostly going to lie to the side of hydronium plus the conjugate base of sulfuric acid. So mostly what you have in solution is hydronium, and that's based off of the leveling effect. that we looked at in the acids and bases chapter. So you could draw either way. Okay, so I'm just going to draw H3O plus, if I can get my iPad to stop moving here. So I'll draw H3O plus like this, and then I'll put in some lone pairs here, and let's draw the first curved arrow, which represents the proton transfer. And then iPad is going on with my iPad. Sorry, seem to be having technical difficulties here. There we go, and I knew it would delete everything. Yep. Okay, so let's start over here. So we've got our hydronium. There we go. So first step is the proton transfer. We'll put in our lone pairs like this. There we go. There's our proton transfer. So what do we end up with? We end up with the protonated oxygen. We sometimes call that an oxonium. So again, I'll draw the shorthand like this. Okay, so now we've created a good leaving group. That's going to leave. And let's draw the carbocation that results. And it's going to look like this. So this is a secondary carbocation, but you see that we can do a methyl shift here, can't we? We can do a 1,2 methyl shift, and that will produce a tertiary carbocation. So then we end up with this guy right here, and we know that we have a proton over here. And so in the first step, we formed water. So now water can come in and act as a base, right? The water can behave as a base because we're in an acidic environment. So it can pull off this proton, and then we're going to form the double bond like that. And there you have it. So those are two mechanisms. The first one got deleted, but it's going to be in the video where we created a good leaving group, and then we had the nucleophilic attack. And then here we had a carbocation rearrangement. So you want to be kind of always on the lookout for rearrangements like that. Well, the last section of 7.13, we looked at this briefly last class, and I just said, well, you want to familiarize yourself with all of the different reactions for a primary halide. Here we have a strong base doing an SN2 reaction. Here we have taking the alcohol and taking HBr. That's also an SN2 reaction to make an alkyl halide. We said we can convert the alcohol into a good leaving group, a tosylate, using tosyl chloride and pyridine. You could do an SN2 reaction with a tosylate because it's a good leaving group, just like an iodide or a bromide or a chloride. So you could make an alcohol that way. What else? We said, okay, well, if this is a good leaving group and we treat it with a hindered base, that's never going to act as a nucleophile. It's only going to act as a base. So you'd make the alkene that way, right? We talked about non-nucleophilic bases, again, like these, doing elimination reactions. If you have a strong base, strong nucleophile, you're mostly going to get substitution. Again, this is a strong nucleophile, weak base, thiolate or hydrosulfide rather. There we go. So you end up with a thiol. This is one that we didn't talk about really a whole lot. It doesn't show up in the book until this section here, but this is an acetate, and this is a polyatomic ion you should know from general chemistry too, right? You have a negative charge on an oxygen like this. So that's going to be a good nucleophile, right? Think about it. It's the conjugate base of acetic acid, which again, you would have seen a lot in general chemistry too. So it's going to be a weak nucleophile, or sorry, a good nucleophile, but weak base. So we'll put here strong nucleophile or good nucleophile, weak base. And so that can do an SN2 reaction. Right, if we draw the curved arrow like this, okay, that can do an SN2 reaction like that to make an ester. And then the last one is using cyanide. And cyanide is also a good nucleophile in a weak base. There we go. With a tertiary alkyl halide, again, you got to remember all these reactions. There's a lot more elimination reactions when you have a tertiary alkyl halide. If we treat that with a hindered base, we mostly get the Hoffman product. If we treat it with a non-hindered base, however, we mostly get the Zaitsev product. Same thing here if we have the tosylate, same kind of thing. What else? We can take that tertiary alkyl halide, we can do an SN1 reaction, a solvolysis reaction with water to make a tertiary alcohol. We just looked at this reaction. We just drew the mechanism of it. This is an SN1 reaction. And the same thing here, if we take the hydroxyl, we can convert it to a tosylate, which again is a good leaving group. So again, you've got to familiarize yourself with all the reactions here and all the reactions on that slide. And the rest of the chapter is more just kind of machinations about ways to do retrosynthesis. So I don't want to go over that in gross and dirty detail. Well, let's say you wanted to make a reaction like this. It says, what reactants would you need in order to make the following compound as a product of a substitution reaction? Well, we just saw that in terms of retrosynthesis, if you were to break this bond, if you were to break this bond here, right, what would you end up with? You'd end up with the acetate ion, which is a good nucleophile, weak base, and then you'd have to have some kind of primary alkyl halide, right, that could do or undergo an SN2 reaction like that. So how would you do that? You know, I mean, you could write it down a bunch of different ways, but, you know, you would say, okay, well, I'm going to start with, we'll say ethyl bromide. And again, if you chose ethyl iodide or ethyl chloride, that's fine too. And then we would treat that with the acetate ion, which we need a counter ion for. We'll choose sodium. Sodium acetate is a very common buffer used in general chemistry. And there you go. That's going to give you your ester. So you would do your SN2 reaction like that. And there you go, my friend. You have made an ester just like that. Now, in terms of solvent, since this is an SN2 reaction, what do you want? You want a polar aprotic solvent. So you could choose acetone, you could choose DMSO, you could choose HMPA. We'll just write acetone. And a lot of times solvents are left out in our textbook, but that's the kind of strategy that you would want to take to solve a problem like that. So with that in mind, let's take a look at question 7.44. This comes right out of section 7.13 in your textbook. It says, provide a synthesis for this molecule shown below, starting with an alkyl halide of your choice. So you can just assume you can have whatever alkyl halide you want, show your retrosynthetic analysis, and then provide a complete synthesis showing all necessary reagents. I'm going to throw this out to my students. Could anybody recommend a good nucleophile that I could use? I'm just asking with the nucleophile because it's a lot easier to describe than the electrophile in this case. But could anybody choose or tell me what might make a good nucleophile if I want to make this compound here? If I want to make a nitrile is a functional group, what would I want to use as a nucleophile to make a nitrile? There's only one possible answer, and I've mentioned it this morning. I'll give you a clue. It's a strong poison. Ever heard of the Jonestown Massacre? Yes, cyanide, exactly. So if we think about making a nitrile, you're always going to make a nitrile from cyanide in chapter 7. So what would we need? We would need cyanide, and then we need to break this bond here. So you'd have what? You'd have this, and then you'd have these two carbons, and then you'd have to have some kind of leaving group here, and then you'd have to combine it with cyanide, right? Because then you could just do an SN2 reaction like that. This is a primary alkyl halide, and this is a good nucleophile, good nucleophile, weak base. So there we go. So what's our synthesis going to look like? It's going to look like this. We're going to start out with this primary alkyl halide, and I'll choose iodide this time. Again, you could choose bromide, you could choose chloride, whatever, doesn't matter. Then, like Mackenzie said, we're going to use sodium cyanide. Okay, and then for a solvent, again, since this is an SN2 reaction, you could choose acetone, you could choose DMSO, you could choose acetonitrile, whatever. So let's just choose acetone again. So we'll use acetone, and that's going to give us what? That's going to give us our nitrile, plus you're going to end up with what? You're going to be also left over with sodium iodide, right? An ionic compound. So we're going to be, we're going to be left over with some sodium iodide as well. And again, it's just an SN2 reaction, okay? You could draw the SN2 reaction all day. You know, you just take your nucleophile and it's going to attack the electrophile. Son of a gun. There we go, right on the carbon like that, and then you lose your leaving group like that. SN2 reaction. There we go. So that's the kind of synthesis, you know, question that I think is a really good one. You have to do a little bit of retrosynthetic analysis here and be able to determine, you know, what would your reagents be. I think it's a very good question. The last question that I had chosen here for section 7.13. And this is the last question in the slide deck. This question 7.45. Again, you could look up the solution in the textbook if you want to. I encourage you not to do that until you've tried it. But this is a good one. It says, which is the better retrosynthesis for this molecule, right? Let's say somebody says, you know what, I'm going to back a dump truck of money up to your house if you could just make me some of this molecule. I need like, 100 kilograms of this, which sounds like a lot, and it is. But if you think about prescription drugs, they're made on the kilogram scale. So if somebody said, I'm going to give you all kinds of money to make this, and then somebody says, okay, well, you can either have molecule A or B as your starting material. Could anybody suggest which would be the better starting material? Would it be A or B? And it's not a trick. As I always say, I'm not a fan of trick questions. Could anybody tell me which one of these would be a better starting material? Yeah. Great. See, all my students have the right answer. Yes, it's going to be B. It's going to be the right molecule to start with, right? If we start with A, and obviously this is the wrong answer, but if we were to start with A, I mean, A is cool. A is a cool molecule. It means it's a nice tertiary alkyl bromide, right? Okay. But if you were to treat this with a strong base, strong nucleophile, like let's say sodium ethoxide, okay, NaOET, right, with our negative charge. Well, the thing is that this is an alpha carbon, but if you look at the molecule, there's beta protons here, and then you also have beta protons here, and they're two different types of beta protons, aren't they, right? You have this type of beta proton in black, and then you have this kind of beta proton in green. So if you ripped off the one in green, you'd end up with this, which isn't the right product. Okay, so you'd end up with that. If you ripped off the one in black, that's cool. I mean, you would end up with this compound, right? You'd end up with the desired compound, but the problem is you end up with a mixture, right? You get mixture, okay? Whereas if you started with B instead, so I wrote out B in blue, B for blue, right? I had that all planned from the get-go. So, I mean, there's a plane of symmetry in B, right? Running down the molecule like this. So there's only one type of beta proton, right? It's only this type here, right? The same thing here. So that means there's only one regioisomer that can be obtained in this specific case, right? You would only end up with the desired product and nothing else, okay? Only product that you would get. So only product formed. So give me a thumbs up if you follow me on this one, or let me know if you have a question, because I think this is a very good question in terms of maybe like a final exam. I mean, your quiz too, but this is the kind of thing they ask on an ACS final or an MCAT. I mean, great. Thanks, Edwin. I mean, both of these compounds, you can make this molecule. There's no arguing that, right? But there's one that's a much better choice, and that would be B, because you only get one regioisomer. Cha-cha? Okay. All right, good. Again, this is the kind of thing you want to make sure that you understand, why it happens, because it's such a good question. All right, I wanted to take a look at some questions, or some of the parts of question 7.76. So if you have your textbook, you can open it up to 7.76. I'm going to open up a blank document, and I wanted to take a look at a couple of the questions from, this is again 7.76, comes straight from your textbook, nothing fancy, right? Let's see here. I want to start with the first question. You have to bear with me because I have to look over my monitor here. So we have a stereo center, and we're using, here we go, potassium T-butoxide. I'll write down B as well, and I'm not going to focus on mechanisms here because the question just says identify major and minor products. So major and minor products. What are they, right? Nothing other than that. Okay, so let's see here. So I have this primary alkyl halide, and I'll treat it with sodium hydroxide. Right, and this is where you might want to use figure 7.20 to help you out. I recommend trying to familiarize yourself with it, or trying your own, best shot to get it before looking at it. So let's take a look here. We've got a secondary alkyl halide, and we've got a strong base that is very hindered. So hindered base. I mean, you never see T-butoxide behave as a nucleophile. It's just too dang hindered. All right, way too big. Okay, so let's see here. If we have a secondary alkyl halide, we know that the major pathway is going to be elimination, right? Again, especially if we have that hindered base. Well, there's two types of beta protons, aren't there? There's the ones in green, and then I'll write down this one in blue. Okay. Now, which one would be pulled off preferentially by a hindered base? It's going to be the one in green, isn't it? Right? If we pull off the one in green, we end up with the Hofmann product, but that would be the major product in this case. So major product. Now, in terms of the one in blue, there are actually two blue protons. And so in order for in terms of the stereochemistry of the reaction, this is not going to be stereospecific. It's going to be stereoselective, right? Because I have these two, you could call them HA and HB, for example. Right? If I pull off one of them, I get a Zaitsev product that's going to be trans. And if I pull off the other one, I'm going to get a Zaitsev product that is cis, like that. So these are going to be minor products. So both of these will be minor products. And it doesn't ask us to split hairs between these two. Probably the cis would be formed in a greater amount, or sorry, the trans would be formed in a greater amount because it's less sterically hindered, but that's neither here nor there. All right, let's take a look at B. We have a primary alkyl halide. Let's write down what we know. We've got a primary alkyl halide. We've got a strong nucleophile, strong base, right? Hydroxide is a very strong base. But since this is primary, the main mechanism is going to be substitution, isn't it? Right? The main product is going to be the product of an SN2 reaction. So we'll draw it with the product of the SN2 would be, where we have the hydroxyl. Again, this would be the major product. But since it's only primary and you do have a strong base, you're going to end up with a little bit of, beta elimination of this proton here to give you what would be called 1-butene, right? That would be your minor product, right? And again, I'm just looking at figure 7.20 or using, my organic chemistry prowess to solve this type of problem. Let's take a look at another one. I think we looked at one similar to this, but it bears repetition. So this is 7.76C. We're starting it with a secondary alkyl halide again. It's got a chiral center, and we're treating it with sodium ethoxide. Okay, so again, we've got a secondary alkyl halide. We've got a strong base, strong nucleophile. Now, what did we say about substitution, right? Nucleophilic attack. We said that when you have a methyl, it's going to be the most reactive. When it's primary, it's also going to be reactive. But once you get to secondary alkyl halides are hindered enough that elimination is always going to be the predominant mechanism, right? So we're going to get some substitution, but it's going to be minor. So let's talk about the elimination first. We've got these protons here or this type of proton in blue, and then we have these ones in green as well. So since this is an unhindered base, okay, so we could put here unhindered. That means that the Zaitsev product is going to be the major product. Now, in terms of the Zaitsev products, I would assume that the one that gives you the trans is going to be the major product because it's less sterically hindered, but we'd get some of the cis as well. And then we're also going to get some of the Hofmann product. But we're also going to get some of the SN2 product as well, right? We're going to get some substitution. Again, if you take a look at figure 7.20 and you look at secondary alkyl halide, you look at strong base, strong nucleophile, you'll see that the major pathway is going to be E2. So this is all E2 products, okay? But there's also going to be some SN2. Now, what do I know about SN2? That when SN2 occurs, it occurs with inversion of configuration. So my ethoxide, if I draw the mechanism, okay, if I draw the ethoxide, okay, remember, the nucleophilic attack is going to be backside attack, right? It attacks from the opposite face of the molecule as the bromine. So since the bromine is pointing out towards us, that means that my ethoxy group is going to be pointing behind the page or the screen like that. Okay, so it seems like a daunting problem, doesn't it? There's 4 different products, but you just got to kind of sort things out in your mind. You say, okay, well, I've got a strong base, I've got a secondary alkyl halide. Substitution is not going to be the predominant mechanism. Elimination will be, and I can form Zaitsev and Hoffman products. I'm going to get the Zaitsev product as being the major product because it's an unhindered base. Okay, between the 2 Zaitsev products, the one that's trans is less sterically hindered, so that would be major. I'm going to get some Hoffman, and I'm going to get some substitution as well. All right, any questions about that one? Because that's kind of like what I would consider, you know, one of the more complicated questions because you have so many possible answers. Of course, if you have a question, just stop me. And don't worry, we're going to look at one that deals with stereospecificity in a few seconds here. Let's try 7.76D. So this is D. We're starting it with a tertiary alkyl halide. So we have our bromine here, like this. And we're just going to treat this with sodium ethoxide. Okay, so if I'm starting out with a tertiary alkyl halide and I have a strong nucleophile and strong base, could anybody tell me what mechanistic pathway would predominate here? Would it be an SN1, an E1, an SN2, an E2? I've got a tertiary alkyl halide, strong nucleophile, strong base. Yes, thanks, Mackenzie. It's only going to be E2, right? Yes, absolutely. You're not going to get any substitution at all. Think about it. You've got a beautiful, beautiful nucleophile, but this is tertiary. There is no way, right? This is going to try to, it cannot do a nucleophilic attack. It's just too darn hindered. It's never going to happen. Okay, so if you've got a tertiary alkyl halide, you can get SN2 out of your mind. It's not going to happen. Can substitution reactions occur in SN1? Yes, under the right conditions, but these aren't those conditions. So the only thing that's going to happen here will be elimination, just E2 reactions. Now, if we have that tertiary alkyl halide, we're using an unhindered base, right? Ethoxide is unhindered. And we've got 2 types of beta protons, right? We've got these ones here in blue, and then we have these ones here in red. So since it's an unhindered base, the major mechanism is going to produce the Zaitsev product. So we'll write down the product of the Zaitsev elimination. There we go. So this will be our major product. Again, this is the Zaitsev product. Zaitsev. And then we're also going to end up with some of the Hoffman product, which will look like this. So this would be our minor product. Okay. Well, let's turn our attention to 7.76E. I think this is a really good one. So we're still on 7.76, and this is E. And we're going to take a look at this molecule. I'm going to abbreviate the aromatic ring with pH like that, which is perfectly legitimate. So here we go. We've got a bromine here. And in terms of our reactants, we've got sodium ethoxide, which again is an unhindered base. It's a strong nucleophile. It's a strong base. Now, since it's secondary, we are going to get some substitution, but that would be minor. The major pathway here is going to be E2. Now, in terms of the protons that can be eliminated, if this is my alpha carbon, on my beta carbon on the phenyl, there's no proton, so I don't have to worry about that. However, I do have 2 beta protons here. I have HA and HB. And so this reaction is going to be stereoselective. This will be a stereoselective reaction, right? Because I don't have a chiral center here. I do have a chiral center here. However, again, since this one is achiral, the reaction is stereoselective because I could remove this proton or this proton. Okay, so I'm going to get a mixture of cis and trans, or E and Z, however you want to look at it in this case. So when I eliminate the beta protons, I'm going to get this compound where it's trans like this, plus I'm also going to end up with this. Okay, so this is the E compound, this is the Z compound, and I'm just using the terms E and Z and cis and trans, you know, assuming that you know what those things mean now. So could anybody predict which one of these would be the major? Do you think it would be the E or the Z product? And again, I'm not trying to trick you or fool you or something. Go with your gut feeling. In this case, because it's just stereoselective. Yeah, thanks, Mackenzie. It's going to be the E. All right, this is going to be the major product because of the steric hindrance here that we would see in the Z product. So those are elimination products, but we're also going to end up with a little bit of substitution as well. And since it's an SN2 mechanism, we're going to get inversion of configuration. So we'll put plus, draw in all our carbons, and then we're going to have some of this ether formed like that. Okay, now we can't get out of chapter 7 without taking a look at question 7.76F. Okay, because you can be sure that this is going to come up on your it's going to come up on your quiz, probably one question, maybe two at most, about this. But now we have two chiral centers, right? We've got a chiral center here and we've got a chiral center here. So this is going to be a stereospecific reaction if we treat this with sodium ethoxide, right? There's only one beta proton. It's this one here, okay, that I have written in red. But remember, in order for the E2 reaction to occur, right, E2 is going to be the E2 is going to be the major mechanism with some SN2. Yes, there's going to be a little bit of SN2. But in order for the E2 reaction to occur, this bromine and this hydrogen have to be anti-periplanar to each other, don't they? So what I'm going to do is I'm going to draw a Newman projection looking down the carbon-carbon bond, and I'm going to look at it from this perspective here. Okay, now if you already tried this question and you looked at it from up here, okay, if you looked at it this way, it doesn't matter. You're going to end up with the right answer no matter what, as long as you solve it properly. So I'm going to look down this carbon-carbon bond going this way, and I'm going to draw what I see. So I'm going to need some space here. So let's draw what we would see. We have our, in the back, we have the phenyl group coming straight down. In the back, we have the bromine off to the left. We have the hydrogen off to the right. And I'm talking about this hydrogen right here, if I call that HA, for example. Okay, now the carbon in the front, this carbon, you have the ethyl group coming straight up. So CH2, CH3. Like that. You have the proton in red. I'll call it HB. You have HB over here. And then you have your methyl group over here like this. Okay, I'll even put CH3. Maybe to clear it up. Now I'll leave it like that. Okay, there we go. So what have I got to do? I've got to rotate the molecule or rotate the carbon-carbon bond so that the bromine and HB are anti-periplanar to one another. So what I'm going to do is I'm going to rotate all of these groups, these three groups, okay? I'm going to rotate them 120 degrees in this direction, which is counterclockwise. So let's do that. And when I do that, I'm going to end up with something. I'll draw it over here like this. So I'm going to have something here, something here, something here. The bromine hasn't changed position. Neither has this, nor has the phenyl. So now HB is going to be over here. My methyl group is going to be up here, and my ethyl group is down here. Now you see that the requirement is fully met. The HB is anti-periplanar to the bromine, so I can do the elimination mechanism. So what's going to be on the same side of what? So once you do the E2 elimination, what do you end up with? You end up with this carbon. So I'll call this one C1. So I'll put C1 here. Then you're going to have a double bond up to C2, which is the one behind it. The one that's C1, you've got the ethyl group over here. Son of a gun. You've got the, oh, maybe I'll just write ethyl like this, okay? And on C2, you've got the phenyl on the same side, like that. On C1, we also have a methyl group over here, okay? And then we have HA going in the back like this. So, I mean, you could also write it like this if you want to. I mean, you've got your phenyl up here. You've got your hydrogen here. You've got your ethyl group here and your methyl group like that. Either way, it's the same thing. Could anybody tell me, is this an E alkene or a Z alkene? this be an E or a Z alkene? Yeah, it's Z. Yep, absolutely. So this is a Z alkene. So again, when you're looking at a reaction that is stereospecific, okay, it's got nothing to do with steric hindrance, right? Because the Z alkene is more sterically hindered than if we were to have the E stereoisomer, right? Okay, it's more sterically hindered, but again, in order to do the elimination reaction, the only possibility is to end up with the Z alkene when the bromine and the hydrogen are anti-periplanar, right? And we could scribble that in here. Bromine and HB are, the word is anti-periplanar. And remember the difference between coplanar and periplanar? So coplanar meant that they were exactly 180 degrees apart, whereas periplanar means anywhere, what did it say, between 175 and 179. So they just have to be close, like very close to being coplanar. Okay, so we're going to form that as our major, this will be our major product, the E2 reaction product, but we're also going to get some substitution. So we'll just draw that like this. So we have our aromatic ring, we have our carbon chain, and we're going to end up with some of this. There we go. So this will be our minor product, which is the result of the the SN2 reactions. There you go. We identified the major product and we identified the minor product. Now, this is why we give you scratch paper for your quizzes, isn't it? Okay. It's very difficult to answer these questions. Some students can without writing down the Newman projection. But if you want to take your time to make sure that you got everything in the right place, I find it's really handy to write down a Newman projection. Okay, there's a cool question I wanted to take a look at that involves going back in the notes here. Where was it? Question 7.55. I just want to take a quick glance at it. I don't want to spend all day on this problem, but I thought it was a fun one. Whenever I see something that's kind of, you know, a little bit outside the box, very, very little outside the box. But it says the following reaction. So you start out with this. So you have this compound, okay? And then you're treating this with 1,2-dibromoethane. So that's this compound. And then it says you end up with something that's C4H8O2 plus you end up with 2 equivalents of sodium bromide. And it's asking, you know, what is this? Okay, what is C4H8O2? Well, in terms of what's going to happen here, right, you got to remember that these are both alkoxides, right? They're in the same molecule, but they're still alkoxides. So here I have sodium plus, right, and I have O minus. So both of these oxides, these are both primary alkoxides. So these are both good nucleophiles or strong nucleophiles and strong bases. Strong base. But these are both primary alkyl halides. So what mechanism is going to predominate here? Would it be substitution or elimination? Could anybody tell me? What do you think would be the predominant mechanism if I have a primary alkoxide, so it's not hindered, and if I have a primary alkyl halide? Would it be substitution or elimination? Primary alkyl halide, yeah, it's going to be SN2. Yeah, absolutely, Mackenzie. Yeah, it's going to be substitution. So what's happening here, and I'm not going to spend all day on this, but it's like you get one SN2 happening here, and then you have a second SN2 reaction happening here. So you get 2 SN2s. Now, if you draw out what the product would look like, okay, look, you've got 2 carbons here. So let's draw 1, 2 carbons. Each have a bond to oxygen. And then you did 1 nucleophilic attack and another nucleophilic attack, and then you have another 2 carbons in between, like that. So you can think about these 2 carbons as being these 2, and then you can think about these 2 carbons as being these 2, like that. So it's like a double SN2 reaction, and you end up with this cool molecule like that. So you end up making a diether, right? This is an ether here, and this is an ether here. Anyhow, I thought it was kind of a cool question. You know, I like questions where they give you a formula and just say, you know, what's the structure? What must it be? Okay. I also wanted to take a look at question 7.7. Let's do something a little more complex. Let's go into I know that some of you really enjoy the, I always get a few emails about the integrated problems, okay? And I usually pick a few problems from the integrated problems for you to look at, but, you know, I don't concentrate on those. It depends on the chapter, I suppose. Sometimes they're more pertinent. But I want to take a peek at a question I think would also be a great question for like an MCAT or something, or this class. Okay, I'm not saying it's not pertinent to this class. It's a totally reasonable problem, but it's saying if you have this molecule. So check this out. This is a very cool question. Gets you to think a little bit. Okay, and I'm sure you can all solve it. It says you're taking this molecule, you're treating it with a strong base, okay, and you end up with a new functional group. We call this an epoxide. Okay, so whenever you have a three-membered ring with an oxygen, that's called an epoxide. So you end up making an epoxide. And the question says, when you take this molecule and you treat it with a strong base, you get an epoxide. Suggest a mechanism for the formation of the epoxide. Could anybody tell me what kind of mechanism they think might be occurring here? Would it be an SN1, an SN2? Would it be an E1, an E2? Could anybody make a suggestion here? There's only one good answer. It can't be elimination, right? Because we don't have a double bond, right? In order to get eliminate, you're right that we're losing the bromine, but there's no double bond, so it can't be an elimination. Okay, like what? Think about it this way. What if we? Yeah, I think it's more like an SN2. Absolutely, right? We've got the oxygen, the hydrogen attached to the oxygen. So if you have a strong base, right? Let's imagine you put this in sodium hydroxide, right? That's a strong base, okay? Well, what's going to happen is the hydroxide is going to abstract the proton like this, and then you might end up with something that looks like this, okay? Where you have the oxygen with a negative charge, and then you have the bromine here. So it's like this. It's like you've got a good nucleophile here, and then you have an electrophile here. So everything's set up in the same molecule, so you're going to do the nucleophilic attack and the loss of leaving group like that, which is going to give you this molecule over here. Now, I didn't look at the solution to this. I usually don't look at those, but I just want to think about it for a second with you guys. I thought you might find this interesting. If you draw the chair, okay, if we draw the chair of this molecule, right, if the hydroxyl is going up and axial, then the bromine must be going down an axial, right? And in order for the elimination or for the SN2 reaction to occur, these two groups actually have to be anti-periplanar to each other, right? So when you deprotonate, you end up with this, okay? You end up with this species right here. But in order for this SN2 reaction to occur, all of these groups, meaning, where's my highlighter? All of this has to be coplanar or anti-periplanar in order for that to happen. Anyhow, I thought you might find it interesting. And again, I think it is one of the problems that I suggested. Okay, what time is it? It's 8:49. Let's take a look at a couple more, and then we'll take a break. I wanted to take a look at some of the questions in 7.77, and I'm sure that some of you tried this question. It was in the list of suggested problems. I'm sure that some of you might have tried even all of these. But I thought we would just take a look at a couple of them quickly. And you should, again, be able to solve all of these problems with relative ease. And I don't mean it's easy, but after you study, you should have that knowledge. So here we go. Oops, I don't know what that is. There we go. Okay, so SH minus. Okay, you remember that that is a weak base and a strong nucleophile, isn't it? Okay, so we've got a secondary alkyl halide, and we've got a weak base, so that means elimination is not going to predominate at all, and but it's a strong nucleophile. It's very nucleophilic. Okay, so what does that mean? The only mechanism that is going to occur is SN2, nothing else. Okay, if you don't believe me, go right over to figure 7.20, look at secondary alkyl halide, weak base, strong nucleophile. Okay, if it's such a weak base, it's not going to abstract any problems, but it's going to be a good nucleophile. So we're going to get the nucleophilic attack, draw a negative charge here, okay? This is called a hydrosulfide ion. It's going to do backside attack, right? Remember, backside attack. Okay, so we're going to get inversion of configuration. So instead of having a wedge, we've got a dash like that. So that's just an SN2 reaction. Another reactant that didn't show up a lot in our conversation last week would have been DBU. DBU is probably the worst nucleophile ever, okay? So, but it's a very strong base. So strong base, and I know in the book it probably says weak nucleophile, but you could even put here terrible nucleophile. Terrible nucleophile. It's so big and bulky that it's never going to act as a nucleophile. So even though you have a primary alkyl halide, okay, even though this is primary and you think, okay, well, if I have a strong nucleophile, then substitution is going to predominate. But I told you this is the worst nucleophile ever. Horrible. So we're not going to get any SN2. What are we only going to get? If this is our alpha carbon, this is a beta proton right here. So all we're going to get is E2, right? Nothing but E2. So we're only going to get this compound. There's no Zaitsev. There's no Hoffman to worry about. There's only one type of beta proton. There's no cis, trans, EZ, none of that stuff to worry about. You get literally one product. And I want you to think about this for a second. Whenever you have a reaction where you only form one product, I say that's a good reaction in organic chemistry, okay? Whenever you can avoid getting mixtures, you are on the track to doing something great, okay? Let's see here. 1C, okay? Since we have C, what happened there? Or someone, what time is it? It's down to the bottom here. Let's take a quick peek at C. So C is a little strange the way they phrase it here. So you're starting it with a tertiary alkyl iodide. You treat it with sodium hydroxide. Right? Hydroxide is a strong base, strong nucleophile, and it's in water. They kind of throw the water thing in here, I feel like, to kind of throw you off a little bit. But water is just a solvent. Whenever you have sodium hydroxide, it has to be put in water. So this is not going to give you an SN1 reaction when you have something that's such a strong reagent. The pathway is going to predominate. So if we have a tertiary alkyl halide, we have a strong base, strong nucleophile. The pathway that's going to predominate would be E2. Now we've got these beta protons here, and we've got these beta protons. Oops, we've got these beta protons here. But since this is an unhindered base, the Zaitsev product is going to predominate. So the major product would be this guy, so 1-methyl cyclohexene. And then the minor product would be methylene cyclohexene, which is this here. Let me take a peek here to see. Whereas in D is an SN1 reaction. So let's take a quick peek at D. So again, this is still 7.77. In 7.77D, we're starting it with a tertiary alkyl halide. Okay, but it says all we're doing is we're putting it in water and we're heating it up. So what's going to happen is that the leaving group is going to leave first, okay, because water is a weak base and weak nucleophile. So we're actually going to end up with a mixture of SN1 and E1 in this case. All right, so we're going to end up with some of the SN1 product. We're going to end up with some of the E1 product, and there's going to be two E1 products. We'll get this one, plus we'll get this one. Hopefully you remember that the E1 is going to predominate, and since this one is tri-substituted, this would actually be the major product. Okay, that's something that we covered towards the end of last lecture. If you've forgotten, you might want to take a peek at that.